well, welcome. And before I start, I wanted to thank the three organizers, actually, there's one who cannot be there, for inviting me to this school. It's a great pleasure to be there. And but they gave me the very difficult task to open the school. So my task is actually double. So this lecture will be more of a general introduction to the school. And therefore there will be more slides than in a normal lecture. The rest will be done more on the board, if I can say. And then there will be two additional lectures on a more specialized subject, which is the physics of 1D system, 1D quantum systems. And there, as I said, this will be more like a traditional course. Whatever is the course, whether it's this one, whether it's the other, never hesitate to interrupt at any time. We are not running a marathon. What I will say, I will say. What I won't say, well, you will find in the literature or you won't find. But the important thing is not the output flux, is the input flux. So if you have any question, don't wait till the end of the session. Just interrupt me at any time. Raise your hand, shout, yell. If you don't do that, the, let's say, past track records show that I tend to accelerate slowly. So if you want not to have me pass the speed of light by the last lecture, just don't hesitate to say, okay, here we don't understand what you're talking about. Okay, yeah, go ahead. So this first lecture is more like trying to tell you a story. After all, you're here, you're starting your PhD. You will hear during 2 weeks something that will prevent you to do hiking for 2 weeks, which is ultra-cold fermions. Okay, why bother? I mean, why this thing? So I'll try to at least give a motivation in this thing, and to help me a little bit, can I do a real-time poll? So first, how many of you are theorists? Okay. How many of you know something called second quantization? Good, okay. And how many of you have heard of something called the Hubbard model? Okay. Course is finished. I'm going. No. Okay, so more seriously, let me start. As was mentioned, I am from the oops, voilà, here it is. I'm from the University of Geneva, and if you want to know more on the activities of the group, I have given you the website of the group here. I'm in a department which is called the Department of Quantum Matter Physics, and actually the very name of the department will be something I will try to explain. I think I have a problem with this contraption. Voilà. In the sense that in this department there are people working, doing experiments in condensed matter, and there are people doing theory on diluted matter, which is what I think most of you are. You're working with cold atoms, not with solids, and I'll try to explain why these two people can be together. Here is a couple of references. Of course, it's far from being exhaustive. There are many more. You have the traditional reference that I'm sure you all know on cold atoms. I've cited only 2 of them. There are many others on bosons, the very nice book by Stringari and Pitaevsky and so on. More focused on things close to the topic of this conference, perhaps a little bit more specialized, were lecture notes that we wrote with Antoine Georges for another Les Ouches lecture a couple of years ago, which I think is also a good introduction. And on a more specialized topic of the 1D, there are some proceedings of a Varena school. Unfortunately, I didn't put them on the web, but I can give the PDF file to the organizers. That's not a problem. Otherwise, I'm sure you can find them in the library. We'll go back to the 1D a little bit later, but here are some general reference. Okay, so let me start with things which I'm sure you all know, which is the fact that people could... Either my ears are too small or... is the fact that one can trap and cool atom using lasers. And I will, of course, absolutely not explain to you how it's done. You will discover all this in the next lecture, the one by Philip. So this is essentially the reason why you have this lecture. It's imperative you know how to cool things with atoms. Sorry, I'm really... Yeah, okay. Attends, non, je vais quand même faire un dernier essai. C'est parce que ça c'est mortier. Voilà. Should be nicer that way. Voilà. Now the wire should not disturb. Okay, so it's of course very interesting to know how one can cool and trap atoms using lasers, but for the purpose of this introduction, I would not care. Here's a little fluorescence image of a sodium ball which is trapped without contact to anything. And of course, the reason you want to have something which is trapped without contact to a recipient is that the recipient will be at room temperature. So if you want to be able to cool, it's like putting an ice cube in a frying pan. It's not a very good strategy to keep the ice cube very cold. So you need to have something which doesn't touch the walls. And as you probably all of you know, since you're already in the field, at room temperature, so let's say 300 Kelvin, one has a speed for the atoms of around 300 meters per second, roughly the speed of sound, and using various tricks that will be explained to you in the, maybe not the next lecture, but the next series of lecture, one can reduce the temperature. So just to give you a scale, in condensed matter, typically people are working at temperature which are of the order of the Kelvin, or let's say 50 millikelvin by using techniques which are called dilution fridge and so on, but it's very hard to go below. And of course, the big breakthrough was to be able to go much, much below, to go down from essentially the millikelvin to the microkelvin, and of course, using more sophisticated technique to roughly the nanokelvin. Let me just show you a little movie which was kindly provided by Emmanuel Bloch. And essentially, okay, this is a CGI representation, but what is in the window here is not a CGI representation. That's the real deal. Let's see if I can start the click. Yep, sorry. Otherwise, I'll do it that way. Voila. So you see a little cloud here which has been trapped, and okay, you see that it doesn't touch any recipient. And more interestingly, you see that when they shut down the lasers, for me it's, okay, as a theorist I find this a remarkable image. Okay, here they are tweaking things, I don't know. But what I find remarkable is that when they release the gas, you see it go, which means the speed of the atoms of the gas is not that great. Otherwise, 300 meters per second, phew, you would not see anything. The cloud would just disappear. So it just shows you that you have speeds which are really low. So, of course, cooling and trapping was the reason why Steve Chu, Claude Quintanucci, Bill Phillips got the Nobel Prize. Again, going from a temperature of the far reach of the universe, which is 2 point something Kelvin, to the micro Kelvin is already something very important. But I would say at the time, the main use of this cold was to get more accuracy for atomic clocks, essentially. And that's, of course, a very important consequence. But so far, no link with condensed matter, and there is certainly no need for fermions at that stage. Okay. Let me just show you that in addition to atomic clocks, you can also do very interesting textbook mechanics experiments, and this is something which is extracted from an experiment done by Randy Hewlett at Rice University. You know, when you learn quantum mechanics, people always tell you, there are two types of particles. There are the bosons, and the wave function is totally symmetric, and there are fermions, and the wave function is totally anti-symmetric, and that's the way it is, and if you don't believe us, change universe. Okay, but can I see it? Well, in solids you can see it, but I'll come back to that. But can you see it? So here is a very nice experiment where you have a trap, which is a parabolic parabolic confinement potential. So the eigenstates of each one of the atoms trapped into the trap are the eigenstate of the harmonic oscillator. So that's not much more than that. They have kinetic energy, p squared over 2m, plus a potential which is created by the light, which is 1/2 of m omega 0 square r square. So each one of these particles can potentially occupy one of the states of the harmonic oscillator and have the corresponding wave function. So if you are at high temperature, they are spread over all the wave functions, all the eigenstates, and so you get essentially the cloud, and this is an image. The color code is, of course, more intensity means more particle. This is a real space image of the cloud. Okay. You take lithium-6, which is a fermion. You take lithium-7, which is a boson, and you notice that their clouds are practically the same. If any, the fermionic cloud is a little bit less big than the bosonic cloud. And then you lower the temperature. And what will happen for the bosons? They just go because they can occupy the same quantum state. The wave function is totally symmetrical. So at 0 temperature, all the bosons go into the lowest eigenstate of the harmonic oscillator, which has the smallest size wave function. So you expect the cloud for bosons to do chuk, 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 and go to the minimum size that you can get. For fermions, the wave function must be totally antisymmetric. So one fermion can go in the lowest state of the harmonic oscillator, small wave function. The second has no choice. He has to go to an excited state, bigger wave function. The third has to go to an even bigger wave function, and so on and so forth. So in average, you don't diminish that much the size of the wave function. And this is something you can see directly on this experiment, that indeed the wave function shrinks because you're not occupying all the very excited states of the harmonic oscillator. But at the end, here everybody, or you're still at finite temperature, but will be very close to the ground state of the harmonic oscillator, while here you're forced to occupy many states, and as a result your wave function doesn't shrink. So fermions on this very simple experiment already show that they have very different properties than the bosons, and of course the fact that you have to occupy many eigenstates in the system is what gives a very strange property to solids, and we'll come back to that. So, but you know, now this is something, I feel this experiment is something that is part of textbook quantum mechanics, because the question of symmetrization or anti-symmetrization of the wave function is not just something esoteric, but you can directly see it in very simple experiments. Of course, I told you, you stop at the micro Kelvin. You can go even colder. I don't know if Philippe will tell you about evaporative cooling or not. He says no, so too bad for you. You will have to do experiment by blowing on your coffee cup to check that you can do evaporative cooling. But if you did it not with coffee cup but with rubidium atoms, then you get the Nobel Prize in physics. And this is what Wolfgang Ketterle, Eric Cornell, and Carl Weimann got. And this time they went to, let's say, nanokelvin, okay, order of magnitude of nanokelvin temperature. In practice, as you probably all know, except for the theorists, this looks like this. And why do you want to go to such low temperatures? The reason is, of course, that, and something that will come in practically all the course, or at least many courses in this week, that if you have the possibility to cool down, and maybe York will tell you how the collisions and so on allow to cool down. So this is another course that will actually explain to you maybe how this type of things work. Then you know that when you have a quantum object, there is something which is very important, which is called the de Broglie wavelength, which is telling you a little bit the extension at which sort of quantum effects are really manifesting themselves. There are two ways you can see very strong quantum effects. One, you have short de Broglie wavelength. Temperature is high. Bring the things close together. This is what you have in solids. In solids, you get one particle, one electron, every angstrom, every 10 to the minus 10 meters. So you don't need a very large de Broglie wavelength to have very strong quantum effects. temperature can be very high, room temperature. We'll come back to that. But because the particles are super dense, you can get extremely strong quantum effects, even at room temperature. If you have diluted matter, one particle every micron, well, you need to lower the temperature. Now you go from 10 to the minus 10 to 10 to the minus 6. Well, you need to change the temperature by something like at least 4 orders of magnitude. So you need to go much lower by at least 4 orders of magnitude to be able to see something. Now, what type of things can you see? Well, you can see, for example, the famous or infamous Bose-Einstein condensation. And if I can start this thing, let me show you here. Oops. Let me show you. No, I don't want this. Let me show you here. Well, not very efficient. Ah, voilà. A little movie that was made by Julien Bobrov. Voilà. So here are a schematic view of atoms, so let's say bosons, which would be floating around, and they of course occupy various eigenstates in the system because they are at a high temperature. And when you lower the temperature, well, hopefully the temperature should be lowered. When you lower the temperature, then there are several things that happen. Of course, the energy of the system goes down, but the Broglie wavelength of each one of the particles is getting larger. And of course, at some point arrives a phenomenon that I'm sure you will hear. In particular, I've seen you have a course on the BCS-BEC crossover, so you will at least hear about BEC. Then all these wave functions collapse into the same wave function, and this is what people call the Bose-Einstein condensation. And this is something that was described by Bose and Einstein at the beginning of the 20th century for non-interacting particles. Okay, so this is what you get here. Now, these Bose-Einstein condensate, they have special properties because if you imagine a fluid which is made of this and which is scattered by impurity, a normal fluid, each particle can be scattered by an individual impurity, which means your fluid will have friction when it tries to go through whatever material you push it to. If you have all the particles which are in the same state, then it's impossible to scatter individually one particle because you violate this condition that all the particles must be in the same state. So one impurity is totally inefficient to scatter particle. The only way you could do it is if all the impurity were scattering all the particles in the same way, which of course is essentially an event which is practically impossible, and this gives the superfluidity phenomenon, which you know very well. Here is a little example of something in helium-4, which was discovered in 1938. Here is helium-4, which is cooled down in a recipient whose bottom is porous, and you see that as soon as it passes the superfluid transition, the thing starts leaking like crazy. And this is an even more fun image. You get a recipient with helium-4, you notice that there is a drop here. It's not because the recipient has a hole, it's just that because there is no friction, the helium can fall along can climb up the wall of the glass and come down because it has a lower energy on the ground than it has in the recipient. If you take your orange juice or your coffee in the morning, it's not climbing the wall and dropping on the bottom, unfortunately for you, because there is the friction. So this is a strange state of matter, and of course this is a state of matter which is intrinsically quantum in nature, and which is also due to the fact that you get many, many particles which are acting together. And this collective phenomena is one of the most difficult problems that one has to treat in nature. But I would say for bosons, we manage. So this was done in 1938 for helium-4 by Kapitsa, Allen, and Misner, and of course in 1995 using rubidium atom by the three gentlemen that we were already mentioning. And here is a plot of the momentum distribution of, so this is a two-dimensional plot, kx, ky, at various temperature of the rubidium cloud. And you see that here you get a Gaussian-like, so let's say a Boltzmann-like distribution. But passing a certain temperature, you see a huge peak that emerges at k equals 0. And this peak tells you that most of the atoms have condensed into one state, which is the state k equals 0. So this is beautiful, and the natural question when you see this is to say, so what? I don't care. Certainly, as a theorist, since this was predicted by Bose and Einstein in 1924, I think, well, this is not cutting-edge theory. You could say it's beautiful experimental achievement, fine that these gentlemen play with their toys, but I don't care. It's boring, you know. Actually, of course, such thought could not be more wrong. But why do we care? Actually, why is it interesting that there are people who are playing with nano-Kelvin stuff and playing with these particles? And to explain this to you, let me digress now. Let me forget cold atoms. I think that most of you, I hope at least, otherwise shout, already know what I told you here, because you're professionals in the cold atom field. What I will do now is to take you in another field, which is maybe less your field of expertise. I'm sure you suffered like anybody else through a 101 solid state physics course, but let me take you now to materials. Let's change gear, let's forget cold atoms, and let's talk about materials. Let's go to condensed matter physics, something nobody knows what condensed matter physics is. Initially, it was called solid state physics. Then the people doing soft condensed matter polymers and whatever, they protested. They say it's not solid. It's not liquid either. So, okay, let's call it condensed matter physics. Okay, now we have cold atoms. So now it's not even condensed matter physics. It's quantum matter physics. So that's this evolution of names. Okay, so let's talk about materials. Materials are fundamental for humanity. It's so fundamental that they are all age of humanity that are named after a single material. You get the copper age, you get the iron age, you get the bronze age. And the 20th century is clearly the silicon age. Because everything that there is practically in this room, every watch, whatever, cell phone that you have, is based on this. It's based on the fact that these three gentlemen, Bardeen, Bratin, and Shockley, discovered the transistor. And this is based on our mastering of the semiconducting, let's say, properties. So this is the replica of the first transistor. And of course, now you know that transistors are everywhere. But the mastering of materials, of the quantum effect of materials at, let's say, the middle of the 20th century is what created the society in which we live today. I'll just give you an example of how the transistor was an interesting societal breakthrough. You all know, of course, vacuum tubes, which were a way to amplify a signal and blah, blah, blah. And this was the way to treat signals before one was having transistors. So here is a computer in 1947, which is called the ENIAC, which was one of the first computers built out of tubes. And this was the most powerful computer of the time. And let me show you a science journal, like, you know, Scientific American of the time. It's called, you will see, Journal of Popular Mechanics. And this is a serious journal. It's not crackpots. And the guy who was writing the article was getting, you know, wild about the future. How wild can you be? 20th century. Well, the ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons, but maybe a computer in the future may have only 1,000 tube and weight only 1.5 ton. All this went to the garbage can because we have the mastering of one specific branch of phenomena, which is what happens in solids. So we want to continue this. We want to have this. Now, how to master materials? What we understand is free particles. You all had a lecture on solid state physics, and you understand very well that if you have free bosons, they all go in the same state. If there are free fermions, they fill all the states, and you have the Fermi level, and you remember all these words, I'm sure. You suffered through them. Okay, it's very nice, but maybe something nobody told you is that if you take any realistic solid, even stupid aluminum, and you compute the energy scale of the interaction of two electrons. Electrons are charged. They have the Coulomb interaction. the energy scale is 10,000 Kelvin, the typical energy scale. Now, the Fermi level in solids, and I hope every one of you know what a Fermi level is, no protest, is also about 10,000 Kelvin, which means that the effect of interactions in a simple metal like aluminum is as strong as the kinetic energy of the particles. So you cannot neglect interactions compared to kinetic energy, and you cannot neglect kinetic energy compared to interactions. So you're in a mess, because everything that has been taught to you in a solid state course, you can take and put in the garbage can, because you have this to take into account. And if you have to solve the problem of 10 to the 23 fermions, which have a wave function which must be totally anti-symmetrized, and which are interacting together, it's a not so easy problem. So how can we do any calculation? And it seems that this is something very complicated, but actually, if we want to describe property of realistic system, there was a guy who came to the rescue, and this person is Lev Landau. And Lev Landau built a wonderful theory that you will hear in the talk of Misha, and this is how you can sort of miraculously make the interaction disappear. And you make them disappear at the price of changing a couple of parameters of your system. So this is a magic trick. There is no other word for it. I will not explain it, of course, but I refer you to the course which will tell you, at least maybe not exactly how the magic trick is done, but at least work you to some of the consequence. It's miraculous. You start from kinetic energy of 10 to the 23 fermions plus full interaction, very strong, whatever. And the conclusion of Landau is to say, just change the mass. Okay, I'm oversimplifying. Just change the mass and then scratch off the interaction term. Then it's miraculous because we are back to free electrons, so we can compute everything. We know then what is a metal, what is an insulator, what is a semiconductor. We can make predictions. So everything which was told to you in solid state physics course for free electrons, you can still use, but you have to use not for real electrons, but for something which is called Landau quasi-particles, which are behaving like free electrons. So forget this, just take your free electron theory and apply it. That's all good and well, and this has very strong consequence. For example, superconductivity, which is one very interesting phenomenon, and which is, of course, the pendant of superfluidity for charged particles, which came from a competition between who was right between three theories on the resistance of metals at low temperature. One prediction was that it should go smoothly to zero because the cold will remove any source of scattering. One prediction was that it should diverge because the cold will freeze everything inside the solid. And one prediction was that it should go to a constant, of course. Who was right? None of the above. So these gentlemen who had the technology to test because they had the cold, this person got the Nobel Prize for liquefying gases. Not for superconductivity, but for liquefying gases. So he had the cold. The same way then cold atoms have the cold. And because he had the cold, he could try this. And he tried it with mercury. And what happened was, of course, a fourth thing, which is that the resistivity would like to go to a constant, roughly, so something like this, but then suddenly drop to zero below a certain temperature. And of course, this mechanism is by now well understood. It has been explained by Bardeen, Cooper, and Schrieffer. It took just 47 years, if I remember, or 46 years, between the experimental discovery and the explanation of superconductivity. But it's now reasonably explained. And this shows you that if you have the possibility to access quantum physics in a material, then you have very interesting things to have. It also shows you that fermions have very unusual properties. This is done with electrons in solids, which are behaving as fermions. Now, if we look at this brainchild of the fact that we can treat solids like free particles, it gave the transistor, it gave superconductivity, because the explanation of superconductivity is that it's coming from the tiny coupling between the electrons and the vibrations of the ions in a solid. But this is a tiny interaction, much smaller than the Coulomb repulsion between the electrons. And the essence of superconductivity is that this tiny vibration is creating a tiny attraction between the electrons. But why should you keep the tiny attraction and throw away the huge Coulomb repulsion? Landau. Because the huge Coulomb repulsion is treated in the Fermi liquid theory and you can forget it. You have changed the mass. But the tiny attraction you have to treat. So without Fermi liquid theory, in a way, there is no rational way to explain superconductivity. And I won't write how many Nobel Prize superconductivity led to. Closer to us, I won't discuss this in this audience, but there is a phenomenon which is called giant magnetoresistance, which was discovered by Fert and Grunberg, and which is how the resistance of a material changes when you change the magnetic field. And these are extremely important fundamental discovery, but the reason I'm mentioning this is because they really change the life of people. Transistor, of course, I don't need to overemphasize this. Superconductivity is used, for example, in MRI equipment. All the magnets, the magnet which is producing the magnetic field for an MRI equipment is just a superconducting wire which has been looped over itself. Current is injected in at the creation of the loop, and then you close the wire. And the current is flowing without any dissipation forever. So you get a fridge magnet, you get a permanent magnet, but which is able to produce fields of order of Teslas. And you don't need any power source except to maintain the code. So this is something which would simply not exist without superconductivity. And giant magnetoresistance completely revolutionized the way to store magnetic information because it provided extremely sensitive let's say, heads to read on magnetic device. So this is things which are all the brainchild of Landau Fermi liquid theory. Indirect brainchild, but brainchild. Free electrons, free particles, free fermions. Other materials, let me skip that. But now we are in the 21st century. We need to understand the materials, the new materials, the materials of the future. We want materials which can harvest heat and produce electricity. We want materials which can get light and produce electricity. We want the opposite, materials which get electricity and produce light. And it's very hard to do this without playing with the spin degrees of freedom of the particles, the charge degree of freedom of the particle, and eventually even the orbital nature inside the solid. So it's very hard to imagine that we can go beyond what has been done without involving interactions. We can, of course, play with a periodic table, mix everything with everything, but if we want to have some predictive power, now we must do what Landau saved us for 50 years of doing. Solve the problem of 10 to the 23 particles coupled together by interactions. And worse than 10 to the 23 particles, 10 to the 23 fermions. Why I'm saying this is because for fermions, even for free fermions, writing the wave function is a nightmare. It has to be completely anti-symmetrized. It's not just the product of the individual wave function. You have to use permutations and blah, blah, blah. So this is a system which is horrible, but this is a very, very fundamental problem. I cannot resist showing you this quote from Dirac, which was in 1929, where he said, you know, the general theory of quantum mechanics is not almost complete. The underlying physical law necessary for mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws lead to equations much too complicated to solve. So of course, the natural tendency, if you read something like this, is to say the fundamental border is either in the infinitely small, you know, understand what is in quarks and blah, 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 or the infinitely large, understand what is at the large scale of the universe. It's completely wrong. It's completely wrong because there is a third axis, which is complexity. If you take even two stupid particles with two stupid interactions, when you go from 2 to 10 to the 23, you get a problem which becomes now not only difficult to write, but which becomes the source of new physics, superfluidity, superconductivity, more generally, any kind of phase transitions. These are things which do not exist if you have only 2 or 3 or 4 particles. So what the community is facing now is the difficulty to solve the problem of 10 to the 23 particles. And why 10 to the 23? Because in a single millimeter cube of a solid, you get more electrons or more atoms than stars in the universe. So this is really something you cannot avoid. Because in a solid, the energy of the last occupied level is typically 1 electron volt, which is 12,000 Kelvin, which is way above room temperature. So a solid is quantum mechanics you can touch. Because if you're at temperature lower than this, the quantum nature of the wave function is important. You cannot treat the particles like classical particles. And this is, of course, just to show you an example, this is a beautiful image taken by a technique which is called STM, which is a tip which is passing a current. And these are atoms which have been put on a ring. They have been deposited, just like with a crane, by the STM tip. And then this is a measurement of the density of electrons on the surface, and you see there are waves. And you understand this very well with quantum mechanics, of course. You have created a potential, and this is the wave function of an electron in a circular potential. Just show you that this wave nature is present. But we need to solve this problem. We need to solve the problem of interactions, because if we don't, we won't be able to master the new materials that we need. And this is a difficult problem. This is a difficult problem analytically. You won't write 10 to the 23 equations, and you won't solve them together. So there are techniques that Misha will explain to you, which are called second quantization, for example, which already allow a nicer way to write the problem. And you would imagine that this is something you can solve numerically, easily. And I don't want to go into details, but again, the very nature of the fermionic problem. For bosons, it's a little bit better. And I think now we have good tools to tackle bosons numerically. But for fermions, the very nature of the problem, which is that the wave function must be totally anti-symmetrized, makes it extremely difficult to solve on a classical computer. So even with computers, this is the Swiss Center of Supercomputers, which have machines which can do 10 to the 15 operations per second. So this is quite fast. The time to solve problems of this category is largely above the age of the universe. Even if you try to solve it for 1,000 particles, not 10 to the 23. So we are facing a wall, which of course people try to break. It's called the sign problem. Sometime you probably heard this thing. It has to do with the anti-symmetrization of the wave function, and I can go back into maybe a little bit more detail telling you what this is. But for the moment, just keep in mind that brute force solution on a computer is not available. So this is the thing we have to face. So what do we do? How to study? Well, this is very difficult. And to give you an example is the famous high TC superconductors. So in 86, these two gentlemen, Bednorz and Müller, who got the Nobel Prize for it, they discovered a new class of materials, which are superconductors, but not at 10 Kelvin, but at 100 and, okay, theirs were 40 Kelvin, but then rapidly it came up to 130 Kelvin, which was a revolution, because 130 is above nitrogen temperature. So it means cooling is now like this, like practically the fridge you have at home. Nobody knows how these materials work. Most likely, the old solution by Bardeen, Cooper, and Schrieffer does not work. I say most likely because we cannot even pinpoint this with certainty. So you have the material, and now as a theorist, you need to answer how does this material work? Because of course, you think that if you understand how it works, you can do better. Once people had the Bardeen, Cooper, Schrieffer theory, it didn't improve so much the TC, but then Brian Josephson came with the Josephson effect. And this has been a revolution in providing, a lot of application of superconductors that nobody could have thought before. But Brian Josephson could not have done the Josephson effect without the Bardeen-Cooper-Schrieffer theory. So here, the hope is that you will get the same. And these are piece of junk. I mean, this is a mixture of yttrium, barium, copper, oxygen. I mean, this is as complicated as you want. So what do you do as a theorist if you have to face a problem like this? Well, you simplify. You try to make a simplified model. So for example, this junk, I decide that the only thing which is important are the part of the materials in which I have the copper, the oxygen, and then I keep only one orbital for the copper, one orbital for the oxygen, and I try to write a simplified model with this. Okay. The problem is that the simplified model is still too complicated to solve. Okay? Then you simplify the simplified model. And you get a simpler model. And this model you cannot solve. So then you start to do uncontrolled approximation on your simplified model. And you find the result. And then the question is the result the consequence of the model, or is it the consequence of the approximation that I did on the model? And because nobody knows how to solve, it gives conferences on high TC where people insult each other, and people say, my approximation is better than your approximation, and it becomes a religious war. Okay? But how do you do? Gives this. Let me give you the simplest model, and you will hear probably in the course of Hélène Perrin, because she will do fermions on optical lattices. And that's the simplest model that you can imagine for a solid. Biologists, when they want to study genetics or whatever, they take a Drosophila, because this is as simple as it gets. When people want to do phase transitions, instead of working on the glyphosate, blah, 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 they take the Ising model. Because the Ising model is the most stupid model you can take, but which still contains the essential ingredient. Well, the Drosophila, or the Ising model of correlated fermions, is called the Hubbard model. 63. So you see? And this is a model. So exercise for this afternoon, solve the two-dimensional Ising Hubbard model. Okay? If you get it, just talk to me. Don't talk to anyone else. So just after 50 years, this model has been solved in d = 1 and d = infinity. And all the rest is pure conjecture. Of course, we think that the d = infinity solution goes down to maybe d = 3 or close enough or whatever. But of course, d = 2 is still, and d = 2 is important because high TC are d = 2. So let me give you the model. It's a very simple model, which I'll describe as words, and you will see the notations that Misha will explain to you will help you understand the little formula that I will write below. So you want ingredients which describe a solid. So you need a lattice, because like you here, you're on a lattice. Now you would say, why do I care about a lattice? Well, lattice is very important because lattice give an idea of filling. For example, here, you're practically one particle per site. Which means if you were exactly one particle per site, because, I don't know if you noticed, but you have an infinite repulsion with your neighbor. You cannot be two of you at the same place at the same time. If the lattice was with exactly one particle per site, nobody can move. You get an insulator. Not because if you didn't have this interaction, you would be able to move. So this is an insulator which comes from the interactions, and it's called a Mott insulator, after the name of Sir Neville Mott, who was the first to understand this and got the Nobel Prize for it, among others. So this is very important to have a lattice and to have a filling for fermions, because the Pauli principle, the repulsion, are acting in a very special way. So you have these particles which can move on the lattice, and let's take the simple quantum mechanics, like two-side problem where particle can tunnel from one side to the next. It's called the tight binding approximation for a solid. So you say I have a particle which has a certain wave function here, but then it can tunnel to the next site, and tunnel to the next site, and tunnel to the next site. So I will write an Hamiltonian, which is just an Hamiltonian of tunneling between different sites. So I don't even want to know the shape of the wave function on the site and whatever. This is too complicated. I just say either the particle is on this site, and then there is a tunnel matrix element to go on the next site. So I can introduce, if you want, a complete basis, which I would call I, which is the particle is on site I, and the Hamiltonian is written like something for one particle. It would be the sum over, let's say, ij, which are nearest neighbor, of I, j. So I project the particle on site j, and then it can be created on a neighboring site I, and I have a certain tunneling amplitude. This caused a lot of problems between the condensed matter and the cold atom community, because in condensed matter, problems are complicated enough, no dynamics. Okay. Now there is dynamics, which has been put back. So calling the tunneling amplitude T didn't cause any problems. In cold atoms, people immediately said, oh, but T is the time. So let's not call this T, let's call it J. Well, nothing wrong with that, except in condensed matter, J is the antiferromagnetic exchange between spins. So after a while, nobody knew what, and it's like electric plug. We need to normalize the notations. Anyway, so to go back to what I was saying, you get here the particles which can hop from one side to the next. Of course, electrons have spin 1/2. So there are two eigenstates, Sz equal plus 1/2, Sz equal minus 1/2, and the eigenstate is conserved when you jump from one side to the next. You have no reason to flip the spin. There are very interesting effects if you do. Maybe Nathan Goldman will tell you about this. It's called spin-orbit coupling, and of course, this has important consequence, but let me skip it. You can have the particle tunnel as you want, like nearest neighbor. You can, of course, put the next nearest neighbor also tunneling, but even without this, we can have this. And this would be free electrons moving on a lattice. And Hélène Perrin will explain to you the solutions of this. It's called Bloch waves and so on. You will get the full solution. I don't want to go into, but let's complicate the model. So this is the model which is written in notations which are the second quantization, where you introduce operators which destroy a particle, and operator which create a particle. So C destroys a particle on side J with a spin sigma, and then it recreates the particle on site I with the same spin sigma. So it describes a process by which a particle tunnels from one side to the other with the amplitude minus T, as we were discussing. The site I and J are nearest neighbor, and the spin sigma is plus 1/2, minus 1/2, which are the projection on the quantization axis Sz. So this is the kinetic energy. Now I need to put the interaction. What can I put as interaction? Well, let's put the simplest interaction we can. Particles only see each other if they are on the same site. So if I look at one site, I have 4 possibilities. Only 4. 0, occupied by a particle with a spin up, occupied by a particle with a spin down, or occupied by 2 particles. Because the other possibilities, 2 spin up, 2 spin down, is forbidden by Pauli principle. And that's a huge difference between fermions and bosons. For bosons, I could put 3 bosons, 4 bosons, 6 bosons, 25 bosons. Of course, the interaction doesn't like that, but there is nothing which prevents. Here, the Hilbert space is blocked here. So you would imagine it's super simple. Well, okay, there is a price to pay, which is the anti-symmetrization of the wave function. The net result is that this is the only thing we can have on the site. So let's say the interaction, this is the only time particle interact. So we'll just say that the interaction is a number, a simple constant, that I call U, which counts if I have a particle of spin down on the site, or if I have a particle of spin up on the site. If this number is 0, or if this number is 0, the interaction is 0. If not, the interaction is U. So this cost me 0, this cost me 0, this cost me 0, and this costs me U. So particles don't like to be on the same side. Just like you have practically U equal infinity. Okay, you're not quantum, but I'm sorry to say, and you're not an eigenstate of the spin SZ. But except for that, it's as good as any. So this is the Hubbard model. And I highly recommend you as an exercise to try to solve this model. It's not easy. You don't even know where to start. So people have devised a lot of tricks to do this. We'll see some of them in the course, specialized to 1D. You will see other tricks in other course in higher dimension. Do perturbation in U, do perturbation in T, do something else. Mean field, variational theory, numerics, you know, people have thrown the book at it. It's still alive after 55 years. Okay, so just to say that this is a very complicated problem. So again, difficult analytically, people have tried to develop techniques to solve it, very difficult numerically. The numerical error is essentially growing up exponentially with the inverse temperature. So the error is exponential of a constant divided by T, which means if you want to go down at good temperatures, then your signal to noise ratio is very bad. And of course, people have tried to develop numerical techniques, and I cite some of them, Monte Carlo, DMRG, DMFT, and so on, but the problem is still alive. So we are still facing this problem of understanding the physics of many particles, many fermions in interaction. So how do we solve? Well, and again, yep. So I didn't say that we don't have any clue of what happens in other dimensions. So for example, the Hubbard model, if there is exactly one particle per site, is essentially solved. We know exactly what is going on. But as soon as one moves away from one particle per site, a little bit like this amphitheater, there are a few holes here, if I look at the empties. And the question is, what happens to the holes? What happens to the holes? Do they go like a Fermi liquid of hole? You can consider the holes as new particles if you want. So are they behaving essentially as free particles with maybe a renormalized mass or whatever? Or for some miraculous reason, do they turn superconducting? Do they turn superconducting even if this interaction U is repulsive? Because of course, if U is negative, if the particle attract, then we know how to solve the Hubbard model. Because then it's back to BCS. Or if the interaction is super strong, you could say the particle form a molecule, and then you're back to having bosons, and this is BEC. And this will be discussed in the BCS to BEC crossover course. That's exactly the solution if U is negative. So if U is negative, I would say no big problem to solve the Hubbard model, at least if the number of spin up is equal to the number of spin down. If you start to imbalance the population, it becomes tough. And numerically, there is no sign problem. But if U is positive, this is where we start having big problems. And there, essentially, although we can control some parts of the phase diagram, it's very difficult to get the full phase diagram. And so the question is still there. Again, half-filling one particle per site, this is a good solution. We'll come back to this in later today or tomorrow. This gives essentially an antiferromagnetic ground state. But beyond that, it's very difficult to know. Are there other questions at that stage? Because in a way, this is the justification, not to say you will solve the Hubbard model for 2 weeks. It's not the point, but just to tell you that the reason why people play with cold atoms is, of course, the fact that we want to have something that makes a simulation of this problem. And as I said, in condensed matter, it's very difficult to do because you don't control the interaction. These models, they are a caricature of what happens in reality in condensed matter because the interaction is long-range Coulomb, not on-site, and so on, which means that you cannot just compare with the experiment because the experiment contains things which are not in your model. So ideally, what you would like to have is an experiment which is a perfect realization of this model, or a perfect realization of a problem that you're trying to solve. Hubbard model. There are many other models in this category. So how do you do it? Well, you do it not in condensed matter, but with another system in which you can realize quantum particles in interaction, but where you have several advantages which allow you to bypass all these problems. And this is what people call quantum simulators. So a quantum simulator is an experiment which is close enough to the model you're trying to solve that you can read the answer directly on the experiment. I give you a quantum simulator for the division. You take a battery, you take a resistance, and you measure the current in the system. The current is the voltage of the battery divided by the resistance. And therefore, if you realize an experiment and you know your voltage, you know your resistance, you have realized an analog computer which is giving you V divided by R. Well, you could say, I can do it with a pocket calculator. Well, for the Hubbard model, the pocket calculator does not exist. So you need to construct the analog computer that is giving you what you want to know about the model. Does it have a superconducting ground state? Does it have something else? Magnetism, something else. And of course, you would ideally like to be able to control your system, and that's what cold atoms are good for. So quantum simulator is exactly experimental system that implements as closely as possible one of the canonical model. And again, the idea is to read the answer directly on the experiment. So one of the major goals of the cold atom community, and one of the reasons in a way that many tools you will learn during this week are focused on fermions, is because for the fermions, we really are defenseless in the real world. And the realm of cold atom is providing not only a way to solve this very important problem, and keep in mind that behind it there is the motivation of real materials, meaning finding device, but also because, of course, it provides beautiful fundamental problems. And I would say this is the main motivation. At the end, you expect that fantastic physics is coming there. And by comparing what you get on a cold atom experiment, you can also hope to benchmark your theoretical method. So it started a love story between condensed matter and cold atoms. And at first, the person who started the love story, or the group that started the love story, was the group of Peter Zoller, because he was certainly one of the first to point that using cold atoms, you can realize virtual solids. The idea is you use lasers to do an interference pattern, then you have a periodic potential. And this periodic potential is made of light. It's not the positive charges of the ions in the solid which is creating the periodic potential, but you don't care. This is a periodic potential. The atoms play the role of the electrons in a solid. They can tunnel from one minimum of this potential to the next. And by controlling the laser, you control the tunneling. So you have control of this, which is something which is very hard to do with a solid. You can apply pressure. You bring the atoms a little bit closer together, and you increase the overlap of the atomic orbitals, but it's not really good. And something which is even more important, the atoms are neutral, which means if the wave function is reasonably localized here, and again, keep in mind that now the distance is not an angstrom here, it's more like a micron. This atom doesn't see this atom at all. There is a weak van der Waals or whatever interaction, but which at the energy scale you're in, you can completely forget. So they can only see each other if they are on the same well of the potential. Which means that these two atoms have an interaction, and this time it's not an approximation. It's an on-site interaction. So instead of this being a caricature of reality because we're unable to deal with the long-range Coulomb interaction, this is really the experimental reality. And even better, and I think maybe York will talk about it, you can modulate the interaction by using a trick which is called a Feshbach resonance, which means not only you get a control on T, but you get a control on U. You can make U positive, you can make U negative, you can make U whatever you want. So this is, again, as good as a simulation. And this was done. This was proposed in this paper in '98 by the group of Peter Zoller. And it sounds like a dream. It's really something where, you know, for a theorist in condensed matter, it sounds like you go to see your buddies in cold atoms and you tell, oh, I have this model. Can you just tweak a few lasers and implement it? And I want a triangular lattice. No problem. I put 3 pairs of lasers and I will give you the triangular lattice. I want an hexagonal lattice. I will give you the hexagonal lattice. So, okay. So it sounds like a dream. The first paper which spectacularly demonstrated this was for bosons, and it came from the Munich group. And I'm sure you all know these people, Marcus Greiner, Tilman Esslinger, Ted Hensch, who got the Nobel Prize for something else, and Immanuel Bloch. And what they did was to simply put a lattice made of light on this wonderful Bose-Einstein condensate that was realized. And, you know, the so what? The so what? Okay, I get this peak at k equals 0, fine. Bose and Einstein told it. Well, what happens if you put a periodic lattice? Then it happens exactly what happens in this amphitheater. Namely, if the lattice is weak, well, bosons, they just go many on the same site and so on, and you get the superfluid. But of course, if the lattice is very deep, then there is not enough kinetic energy to overcome the repulsion that exists on each site. And it means having 2 bosons on the same site is too costly, so a particle cannot move. And if a particle cannot move, the superfluid is gone. And you lose the peak at k equals 0. Gone. So you get a transition which is entirely induced by interactions, here by the reduction of kinetic energy. They could not modulate the interaction, but they changed the kinetic energy. So they changed the ratio U over T, if you want, between a superfluid, which has a peak at k equals 0, and an insulator, where you get exactly 1 boson per cent. So this was a spectacular demonstration that one could indeed use these cold atomic systems as quantum simulators for dealing with property of interacting material. And it sounds that one has perfect control on the model. You can change the interactions, you can change the strength of the tunneling. This is there. You can change the statistics. If you take, for example, lithium-6, you have a fermion. If you take lithium-7, you have a boson. You can also play with things which do not exist in nature. Bosons with 2 internal degrees of freedom. When I say don't exist in nature, I mean in condensed matter. Helium-4 is a boring stuff. No internal degree of freedom. What happens if your boson has some internal degree of freedom? Well, technically here you can realize. Let me show you the momentum distribution of bosons, which you see at various temperatures. And you see that the peak at k equals 0 is developing. What happens if you replace this by fermions? Well, you will get 3 fermions on the lattice, and all states below the Fermi level will be occupied. So you expect that the distribution is a box. And lo and behold, this is what you see. So all states here below the Fermi level, which on a square lattice, the full band is a square, okay? And you see that you get, we'll come back to this more with equations, but you see very clearly the box. So you see very clearly the difference between fermions and bosons on the lattice. You can change the dimensionality, and that's something which is very important. Because of course, we want to understand what are the effects of being in 3D, in 2D, in 1D. It's not just theoretical interest. It's also because, and I'll come back to that when I attack really the 1D lectures, people want to miniaturize much more. So the more you miniaturize, the more you have to worry about doing physics in tiny regions, in 0-dimensional states, in 1-dimensional states. So here you can play with the dimensionality. If you put here counter-propagating lasers, you can put a periodic lattice here which will be so high that particle cannot go from this place to this place. And then you get, if you do it in the 2 directions, you get a set of tubes. Which means that here your particle will move essentially in 1 dimension. If you only put 2 counter-propagating lasers, you get a set of pancakes. And then you get a 2-dimensional system. So this is just a few examples. I won't go into this, but just to show you that people played with that. Here is a paper by Jean Dalibar's group where they played with the cold atom system to solve or study something which is, I'm sure you heard about, which is the so-called Berezinski-Kostelis-Thouless transition, for which Kostelis and Thouless got the Nobel Prize in 2016. And this is something for which you need a two-dimensional system, and Jean played with this. Here is some other experiment in MIT, where they were trying to study a superfluid. And how do you study a superfluid? Well, one way, you take a spoon and you put it in the fluid and you start rotating. And if it's a normal fluid, the whole rotation is carried in the fluid. But if it's a superfluid, the rotation will only penetrate under the shape of quantized vortices, and here is the direct observation of these vortices. So this is nice because you can observe things directly. So Hubbard model, since I was mentioning, of course, there are many, many things we will hear in the mini course, but let me just show you what happened for the Hubbard model. There was a burst of activity in 2008 by mostly the group of Immanuel Bloch and Tilman Esslinger. Here is a measure that was performed in the group of Tilman Esslinger, which again sounds like a simulation, but is an experiment. You measure the number of doubly occupied sites, something you could never do in a condensed matter experiment. You don't have a probe which goes inside the solid and tells you this site is doubly occupied. But here you can. So you can count how many sites here have two particles compared to all the other cases you get. And of course, if U is large, you would expect that this number stays very low. And this is what they observed. This is for U equals 0. You see that when they start filling, this is with the atom number, when they start filling the system, the number of doubly occupied sites grows. If U is large, or reasonably large, then it stays essentially 0. So what they proved here, and I don't want to go into detail, is that at least for a while, they stayed with one particle per site. So they stayed with this Mott insulator state we were talking about. Of course, that's a little bit short because this we know how to solve. But it's difficult to go beyond. Okay, this didn't prevent science from saying that, yeah, quantum simulators. And if you want to go beyond, you can even get closer to something which looks like a simulation, and this was done by the group of Marcus Greiner, first for bosons, shortly after 2009, where you can take an image of what is going on. So you can take a photograph of what is going on. So here is a real experiment where on each site you say, I have an atom or I don't have an atom. This is bosons. This is the bosonic version of the Hubbard model. And so by this image, you can do a lot of things that would be impossible to do because if you have only a local probe. Here you can really compute correlations. You can say what is the probability that if this site is occupied, another site is empty. And so there are a lot of informations that you can extract from that. And more close to us, 2017, here is the same microscope, the same thing, which has been done this time for fermions. So this is really observing fermions on the lattice with a spin. So let's say spin up is red, spin down is blue. And being able to give you a snapshot of what is going on in this system. So this is just to show you where the border or where the challenge is. These people are trying to indeed study the phase diagram, to study the properties as a function of temperature and as a function of the filling of this lattice. This is what we were discussing. On this axis, we know exactly what is going on. On this axis, when they start to be holes on the lattice, we don't know. What is written here is the phase diagram of high TC superconductors, which of course we don't know if it has anything to do with the Hubbard model. But it's tempting. So here is what is the phase diagram. Numeric stops here, essentially. Oh, not on this axis, but here. Numeric sort of stops here. And you see cold atoms now are able to go there and move on this axis. It's still a little bit high. You would love to be there, but already the experiment can give information of what is going on there. So for that, one needs development at the experimental level, and one needs development at the theoretical level. And that's what the course that you will get during this school is about. Not just the Hubbard model, of course. There are many, many other problems that I didn't talk about. But this is essentially a good example, or maybe the most easy example to explain of something for which cold atoms can help condensed matter, and at the same time condensed matter can feed back onto cold atoms. Here is a photograph of what is the image which is there. A white square is, let's say, a red atom, and a dark square is a black atom. What would you say? This is, let's say, low temperature. This is somewhere there. What would you say about the ground state? Can you immediately spot one remarkable property? Yes, it's an antiferromagnet. You see it down, up, down, up, down, up, down, up, down, up. So you see very well that on this line, the ground state of the Hubbard model is an antiferromagnet. And you see also that, of course, if you increase the temperature, the antiferromagnet disappears, because now the thermal excitations are sort of flipping the spin. Of course, now what you would like to know is what happens if you dope. Still not there, but people are working very hard on this. There is a recent paper by the group of Brian DeMarco, I think, on the subject. I wrote a little news and views, let's say, on this. So here is the quantum simulation aspects. Now, there are many, many other things one can do: exotic lattice, novel probes, perfectly controlled disorder, dynamics. And that was already in the first paper by the Munich group. This is something that cold atoms can do very well. You get an isolated quantum system, not something in which you get energies that can leak out by zillions of channels, but an isolated quantum system. And on this isolated quantum system, you can turn on the lattice, turn off the lattice. Something you cannot do in a solid. I cannot remove the lattice just for the pleasure of it. So you can study out of equilibrium physics. You can study phenomena that are intrinsically out of equilibrium. What happens if I add the insulator and I remove the lattice? The system ground state is now superfluid, but how does it go from being an insulator to a superfluid? This was done already in the 2002 paper. They did it. They could switch off their laser and monitored how the system evolved. Now it's coming back to condensed matter, just as an information. The problem in condensed matter is that time scale are femtoseconds, if you want to do that. But now people have tools. And one of these tools is called the free electron laser, which is an extremely efficient, and I don't want to go in detail, source which allows you to probe at very short time scale condensed matter. And people have started to play the game with solids. Put the solid out of equilibrium, distort the lattice, and then very rapidly measure before anything had time to decay. But in cold atoms, it's something which is the bread and butter. So people have played with this. And of course, they have tried, now that interactions are local, you can try to put back longer range interactions by playing with atoms with dipolar forces, or by playing with Rydberg atoms. Now, this is the dream. And of course, if it was such a dream, everything would have been solved long time ago. Now, the simulator is not perfect. It's not that it has errors. It's like my division simulator. If I take the voltage and I divide by the resistance, of course I make a small mistake on the voltage of the battery, and I make a small mistake on the resistance. But it's not the point. The worst thing, and for me that's my worst nightmare as a theorist, and is the fact that the first experiments were done in a confining potential. You need to prevent the atoms from just falling down. And you remember the Randy Hewlett experiment I showed you? I told you the potential is like a harmonic oscillator potential. Well, actually, it's more or less always that. So the particles are subjected to a potential which varies as r squared from the center of the trap. It's a nightmare. Because it means in the same system, you will get things with different densities. And we are talking about phenomena which crucially depends on the density. I told you density is 1, you have an insulator. Density is 1.2, maybe you have a superconductor. What happens if you have everything in the same sample? What do you see? And this was really a nightmare, in the sense that there was no homogeneous phase. If you take a phase diagram, for example, this is repulsion, this is kinetic energy, where you get the insulating phase, you get the superfluid phase. Well, actually, your system contains everything here. Here is density profiles. Superfluid, insulator, whatever. Too short to be a superfluid, too long to be an insulator. Called the wedding cake structure, you know, it's bullshit. So this is a disaster. And this, of course, means that if you want to understand the experiment, there is only one way to do. You cannot read anything on the experiment by itself, because it's this. It's like if you took a perfectly good meal, you put it in a broyer, I don't know how it's said in English, a blender, and then you serve it and say, okay, separate the meat from the potatoes. And the only way you can do it is to do it in the reverse way. You solve the problem, and then you apply this thing by using local density approximation, whatever. And then you give the curve to the experimentalist, and then they can compare. This is face recognition. But then it means the quantum simulator is able to solve problems you know how to solve on a computer. So it's totally useless. So you want to get rid of the trap. And this is done. Now, this is at the stage where the community is able to get rid of the trap. Here is the experiment I showed you. The potential has been engineered here to be flat. So I used to say that I had 3 wishes for the cold atom community. The first wish is get rid of the trap. The second wish is get rid of the trap. And the third wish is get rid of the trap. But this is done. Not by all groups, and there are experiments for which the trap is not a problem. I mean, don't get me wrong. But what I mean is that for this type of issues, there are several groups. There is a group of Zoran Hadzibabic in Cambridge. There is the groups of people who have the quantum microscope usually can also control the trap, for which now one has more or less solved this problem. But this is still not perfect. So main point to improve. The inherent inhomogeneities, some big point. Temperature. As probably York will explain to you, bosons thermalize pretty well. One of the reasons they thermalize well is because they interact well and so on. And so you can cool bosons pretty low. Problem with fermions, you can cool them pretty low in absolute number, but it's not what counts. What counts is the temperature compared to the degeneracy temperature of the Fermi gas, TF. In a solid, EF or TF is 1 electron volt, which is 12,000 Kelvin, and experiments are done at 1 Kelvin, which means you're looking at phenomena for which the temperature is 10 to the minus 4 of the degeneracy temperature. And that allows you to see, for example, superconductivity, which is at 10 Kelvin. Okay, cold atoms, the best experiments for the moment, have temperatures which are of the order of TF over 20, more routinely TF over 10. So it's like if in a solid state lab, they were performing experiment at 1000 Kelvin, 3 times the room temperature. So you melt the sample, you melt the cryostat, you melt the experimentalist, melt everything. And of course, if you had interactions which are as strong as in a solid, you would not see anything. The thing which saves the quantum simulator for cold atoms is the control on the interaction, because then you boost the interaction and you bring the phenomenon above the temperature. So it's not too bad, but it's definitely something that can be improved. Hence the necessity to understand how to cool and how one can imagine better phenomena to cool. In this experiment that I was showing here, they took special care to have the interesting region here surrounded by a reservoir of other particles which provide the coolant, if you want. So it's a very complicated situation, but learning how to cool, having the cold, is really an important ingredient, especially for fermions. And in some occasions, I would say the necessity to probe some things are important, but I won't go too much in detail. I think this will be discussed later, either in my course or in other courses. But just to say that cold atoms provided some very exciting things because they brought probes that do not exist in condensed matter. So they force people to think in a different way. On the other end, there are some things that can be measured in condensed matter that they can't measure. And so trying to develop new probes is certainly something which is important. Okay. Let me stop here. I think this was just to motivate a little bit the 2 weeks on fermions that you will endure. Let me skip this. It's not really important. So just to conclude this introduction part, I think one big challenge that the study of fermionic cold atomic system provides is this unique possibility to study the very complicated problem of interacting fermions in a controlled environment where you can control interactions, where you can control temperature, where you can control kinetic energy, where you can put whatever lattice you want, no vibrations of the lattice is the lattice, and so you can realize quantum simulators. But of course you can go beyond quantum simulators. You can invent new things like switching off the lattice, studying out of equilibrium physics, putting weird lattice, studying spin orbit coupling, artificial gauge fields. I'm sure Nathan Goldman will tell you about this. He will talk about topological effects, which cold atoms allow to generate, measure. This is really something fantastic. So in a way, this is a complement, or this is something which replaces in part simulations, because there is such a precise control on everything. But of course, these are real experiments. So ultimately, physics is an experimental science. So they provide the thing. But in a way, they provide realization of things which are so close to models that we study that this is really a useful tool. So again, I wanted to show you and to motivate you by this remarkable condensed matter cold atom interplay, that the interest, especially for fermions, is to serve as quantum simulator and of course beyond. They have provided this remarkable new way to think and to measure. For example, the equivalent of the microscope does not exist in any measurement I know in condensed matter. And I think really now one is at a border where the things have been, it took 15 years, but you're at the right time, because I think that's the moment where things will explode, will really go on. And I think there will be many important developments in this line coming through. So, as one says, I think it's the beginning of a beautiful friendship. And on that, I stop this lecture, this introductory lecture, and take questions if you have any. Yep. Yes. So the temperature are again always in the range of nanokelvin and so on, but for bosons, essentially the temperatures compared to chemical potentials, which is a little bit the equivalent of the Fermi energy for fermions, are much better. And so most of the phenomena you saw, for example, the Bose-Einstein condensation, the peak is very well developed. If I try to show you superconductivity or for fermions, no way. Unless you put an interaction which is of the order of the Fermi energy. In which case, you will see superconductivity. The MIT experiment that I showed superconductivity, but with an interaction which is extremely high compared to the Fermi energy. So getting in the relatively weak interacting regime is much more difficult for fermions than for bosons. So I would say for bosons, temperature is usually not an issue, except for experiments which do not have control on the interaction, because then the only way to reinforce the interaction is to kill the kinetic energy by making the lattice more deep. In which case, if you kill the kinetic energy too much, then the temperature becomes an issue again. So there are experiments that, I will show them to you, for example, on disordered systems, for which indeed the temperature is an issue, but because people had to put such a deep lattice that you kill too much the kinetic energy. But if you have fermions in a weak lattice, if you have, bosons in a weak lattice, usually temperature is not an issue. The problem with fermions is that most of the energy scale you get very rapidly become extremely small if the interactions is not very large. For example, superconductivity, the critical temperature for weak interaction is essentially exponentially small in the interaction. Again, most materials in nature, in condensed matter, have a TC of, let's say, 10 Kelvin, while the natural scale in the solid is 10,000 Kelvin. And the reason is this exponential dependence. So if you want to beat that, either you make U large, and you can, or you lower the temperature. The cold atom, for the moment, they cannot lower the temperature enough. So if it's on the attractive side, you just make U large. On the repulsive side, you don't control what is the scale. Making it more repulsive is probably not going to help. You have to find the right balance. The same way, for example, for the magnetism. I showed you this magnetism here that was observed here. Okay, the reason why you get the magnetism is because there is a phenomenon which was discovered by Phil Anderson, which is called superexchange, that there is actually an effective Heisenberg Hamiltonian that is created, but with the exchange J, which is essentially 4t squared over U. We'll come back to this mechanism. Okay, you see that if you make U super large, you kill J. And if the temperature is of the order of J, thermal agitation will remove the antiferromagnetism. On the other hand, if U is too small, the system is not an insulator anymore, so all this model collapses. So there is an optimal value of J of the order of 10, but then if this is 10, it means that J is at best 0.4 times T. And this becomes dangerously close to the available temperatures. So there are constraints which are linked to the nature of the fermionic problem that makes temperature annoying, let's say. Are there? Yeah. That's a good question. Now I don't remember whether they cheated and they ensured that the center one, because they can also do nasty things, but that's a good question. Or whether they simply selected images. I think this is the correlations. So the correlation at the center is so they take a reference which is 1 point. It's not the center of the system. It's the correlation between what is at the center and what is at 0 site, 1 site, 2 sites. So the correlation at the center is always perfectly 1. Actually, you see, you see that here you get magnetism on this scale, here on a smaller scale, smaller scale, smaller scale. So it tells you that the correlations are decaying with a characteristic length scale from the center. Sorry. Yeah. That's a good question. I can give you a physical answer, or I can give you a technical answer. So the physical answer is that at half filling, the answer is very transparent physically. You get 1 particle per site. The repulsion, if it's large, prevents anybody to move. Then the only thing that can happen is that the spin degree of freedom can change, and therefore the effective model has to be something like this. So you simplify the problem from a very complicated problem which involves charge and spin to something where only the spin degree of freedom remain. On a square lattice, the problem is easy to solve. On a triangular lattice, this Hamiltonian is a nightmare by itself. On a Kagome lattice, it's a completely open problem. So it's not that it's trivial to solve. It's trivial to solve at half filling on a bipartite lattice. So it's still a complicated Hamiltonian, but simple enough. On the technical side, the point is that if you're on a bipartite lattice and exactly with one particle per site, sort of miraculously, the signs that you get in the numerical simulation compensate, and you don't get this sign problem anymore. What physically does it mean? It means once your particles are localized, they are not fermions anymore. They become identifiable by their position. So the anti-symmetrization of the wave function does not exist anymore. So you're dealing now with a problem which is still quantum, but not with fermions. And actually, a spin 1/2 is a boson. Because you can say if the spin is down, it's like nothing on the site. If the spin is up, it's like one boson on the site. And you can check that by doing this, you respect all the commutation relation of the Pauli matrices. The only limit is that you cannot put more than one boson on the site, because it's down or up. And it's what you call hardcore bosons. So bosons with an infinite repulsion, so that you don't put two on the side. So at half filling, actually, it's like if this problem went from fermions to bosons. And we know how to solve bosonic problems. Why do I call them half filling? That's the jargon of the thing. Why do I call them half filling? Because if I have fermions, and let's say I have a couple of sites, the best I can do is to put two particles on each site. So each site is now with two particles. If I have only one particle on each site, I have half the filling. This thing is half the filling of this. So it's half filling compared to one species. So one species is occupying one site over two. So each spin up and spin down has a density 1/2. But of course, at the end, it's one particle per site. Are there other questions? Well, I think we are in time for the break, exactly. And I promise the next two courses will be more with equations and things than slides, because I think slides is too much.